Hello everybody, welcome to We Shape the Light, your podcast dedicated to beam shaping and its application in various industries. Today we're going to talk about laser macroprocessing, or in other words, manufacturing parts at a super-millimetric scale using lasers. My name is Julien Bayol. I'm product manager assistant at Kai Labs, working on the Canonda product line, which is devoted to laser material processing. During my studies of mechanical engineering, I developed an interest for innovative manufacturing processes, and this is actually what brought me to laser material machining, and more precisely, to macroprocessing. I remember the first time I heard about additive manufacturing, how you can build a part from practically nothing using the energy of a laser to melt and agglomerate the matter. I loved how it paved the way to many new possibilities for manufacturing more complex, lighter parts. Today, I'm glad to have a talk with Guillaume Bouquet, our laser market specialist and international sales manager at Kai Labs for material processing applications. After an insightful talk about microprocessing in the third episode of this podcast series, We Shape the Light, I asked him to record our discussion about macro machining so I can share it with you all. Hi Guillaume, how are you today?
Hey Julien, I'm doing fine, thank you.
Well, thank you for being here today. I'm glad you're taking the time to answer my question and share your experience with me and our audience. Can you remind me your professional background? Why are you so interested in macroprocessing?
Well, during my past experience, Julien, I actually, spent the last 21 years back in optics and photonics with basically different types of companies, from photonics with some CCD and matrix sensors for digital imaging, and several other companies for microprocessing and laser manufacturing is concerned. But I guess there is a real big challenge nowadays that is pretty new, coming from the microprocessing side down to right now the macroprocessing side. There's a ton of new applications that are pretty much exciting.
And what interest do you have mostly for macroprocessing?
Well, what's really exciting about it is how light can be shaped using hundreds of watts, up to tens of kilowatts basically, for lasers to improve the yield and increase the productivity of these processes. I visited our partners at the Institut Maupertuis, for instance, where I could sense all the capabilities and the new challenges there are with beam shaping, ranging in terms of welding, cutting, and indeed additive manufacturing. We carried out welding tests with them using a millimeter outer diameter ring beam profile.
Wow, that's impressive to imagine this amount of power concentrated in a few millimeter beam. But more precisely, how would you define laser macromachining?
Well, to answer your question, microprocessing is about the use of multi-kilowatt CW lasers to machine parts at a higher dimensional scale as opposed to microprocessing. Typical dimensions vary from a millimeter to many meters when, for instance, a ship part is welded.
So you're talking about shipyards, but what are the other industries concerned by these processes? What interest do those industries find using laser?
Well, the versatility of lasers provides the ability to answer opposite objectives. High production rates for the automotive industry versus reduced volumes and very high quality required in aerospace. About aerospace, for instance, lasers can adapt to several processes, meaning they allow substantial manufacturing cost reduction. Any industry which has to make mechanical assemblies might be concerned by laser microprocessing, such as automotive, for instance, used it for several years. Microprocessing has been used for several years since the 90s. E-mobility is using laser at many stages for lithium-ion batteries manufacturing, for instance. Shipyards, just like I mentioned, use big metal sheets assemblies or cranes manufacturing as well.
What are those macro-scale processes more in detail? What has been the starting point? I guess that the use of laser for macro processes has come a long way. What's about it today?
Well, historically, famous processes have always been welding and cutting of stainless steel. If we have to consider those two applications, for instance, let's start with, number one, welding. The first application with such lasers dates back 30 plus years ago, when high energy density was used for keyhole regime generation. The laser energy provided causes the molten pool to boil, and the metal therefore begins to vaporize. The vapor creates a vapor-filled hole called a keyhole, a kind of a bubble basically that pushes the molten metal to either side. This keyhole moves along the weld at the same speed as the beam and has the effect of amplifying the transmission of the laser energy by reflecting on its walls. Let's consider now the second application, which is cutting. The high power, or so-called HP lasers, are focused on a small area, bringing very high energy density on the surface where metal melts and then gets plasmonized on a small thickness, allowing the metal part to be cut.
I have also read recently about the use of laser in automated fiber placement. Do you have some insight to share with me? And maybe about other innovative applications that you found interesting?
Well, yeah, you're absolutely right here. Welding and cutting are the two first applications, but other niche applications have risen up, just like automated fiber placement, AFP, mainly used in the aerospace industry where composite fiber tapes are deposited on a mold to manufacture a part layer after layer. Basically, the used laser heats up the fiber tapes during the deposition. Well, besides that, new super innovative applications have come to birth, like for instance additive manufacturing, with for instance laser powder bed fusion application, which consists in the selective fusion of a metal or polymer powder where a laser is used to manufacture a part layer after layer. This application is a new developed process answering some of the automotive industry challenges. Another application is wire laser additive manufacturing, or WLAM, where a metal wire is heated up by a laser and deposited to form a part, in the same way as 3D polymer printers that are widespread for home use. Another of these applications is currently surface texturing, where a shark skin effect is machined onto a part with a high-power CW laser to improve the aerodynamic of wings for aircrafts or boats' hull, for instance.
I understand that laser macroprocessing is definitely widespread in the industry. It's a solution to various manufacturing uses. Do you know what are the challenges the industry is facing nowadays with macroprocessing?
Well, you're absolutely right here. Let's get back to what we previously talked about. Welding, as an application, faces major concerns that have to be answered. Number one of them, improving welding quality, since keyhole regime somewhat causes instability, has to face spatters. Spatters have to be reduced drastically, if not totally. Process repeatability is a big concern, leading to high production with a goal that is to reach a better return on investment. Number two of this is actually improving welding performance. That has to be addressed so as to increase laser penetration into materials thickness to reduce manufacturing time. But there are other concerns as well. One of these goes with automated fiber placement as an application that is oftentimes confronted to complex and large parts with high curvature. This process requires some tooling footprint and low weight so as not to be cumbersome and reduce the moves and the precision of the used robotized arm that has to be maintained. When it comes down to additive manufacturing, increasing the yield is the challenge so that it becomes an industrial standard enabling mass production. New materials, nickel-based superalloys for aerospace for instance, cannot be easily processed for cracks are generated way too much.
That's interesting. It seems like at Skylabs, we shape the light. I deduce that shaping laser beam can be the answer to those challenges. How can beam shaping enhance macroprocessing in those fields?
Well, once again, you seem to be 100% right here. Well, as far as welding is concerned, shaping laser beam with a ring profile such as our Canunda HP for high power offers allows a better stabilization of the fusion bed and the generated keyhole, which leads to an improved quality. No spatters any longer and a hardened strength of the weld. But besides that, our weld bead is larger and smoother, hence a higher quality as opposed to other technologies available on the market. We've actually proven that with the Institut Maupertuis, that our multiplane light conversion, or so-called MPLC technology, used in the Canunda HP ring shaper provides in a way that is more robust as a process on stainless steel, thanks to its extended depth of field and the removing of any focus shift. Another example, for instance, as far as welding complex materials such as copper that is highly reflective renders this process pretty difficult. Because, well, basically solid copper has a higher absorption in the green or the blue wavelengths in comparison to near-infrared. But the absorption in the near-infrared increases when the keyhole is initiated. Well, as a matter of fact, let's remember as well that green-blue lasers are not as commonly available or widespread as disc or fiber ones emitting in the near IR would be. So laser beam shaping is definitely the solution to bring sufficient power onto a material so that basically the keyhole be initiated while it makes it possible to keep an utmost stability, to avoid spatter, and generate higher quality, hence reaching a better and a faster return on investment.
Okay, thank you. And what about the other application we talked about before? Maybe IFP, for example?
Well, eventually, automated fiber placement requires the application of a homogeneous and selectively applied energy with a high level of accuracy over the being deposited fiber. That is why using a sharp rectangular top hat shape drastically enhances the quality of this process. For instance, no resin drop, improved adhesion or cohesion between the layers, and an improved mechanical property on the material in the end. Consequently, what has a major importance as well is the compactness of beam shapers like ours, to reduce footprint and allow an easy mounting on a robotized arm that is thus enabling this manufacturing for deeply curved parts. To give you a better idea, let me tell you one story that I happened to live basically a couple of weeks ago. These few weeks ago, we were delivering our first Canunda HP top hat shaper module at a customer's. This customer has an end user that really wanted to buy another system just like the first one with our beam shaper inside, as he could hardly believe his eyes how much more compact the entire system footprint had become.
I guess there is a lot coming more in macroprocessing at Skylabs. Can you tell me a bit more about the next innovations Skylabs will bring to the macroprocessing market?
Well, that is a good question, Julien. We've just talked about additive manufacturing and the fact that it's part of the future of industrial manufacturing by means of laser processing. It's addressing multiple markets such as medical or aerospace. It's a market that's very widely open to innovation, and the integration of beam shaping is the next step to improve these processings, both in terms of yield and productivity, just like we discussed. We already have a few projects to answer your question coming regarding additive manufacturing, and we have a few exciting new developments, I get to admit, in terms of, this range we have called Canunda HP, providing new shapes dedicated to new applications that we have to address. Indeed, we're willing to keep participating in new projects to expand our understanding of the subject, basically, and expand our market reach. It's a pretty broad domain. Our new favorite topic is copper. Within a year or so, the automotive industry will make a statement regarding the best processing solution on whether it'll be a blue, a green, or an IR wavelength that will be the standard wavelength used for copper welding with regards to the automotive industry. Each one of these wavelengths has challenges to overtake, and we will actually try to be at the innovation forefront to figure out the best way to improve each color process with our Canunda HP beam shapers.
Thank you, Guillaume, for your time and great explanations. I hope that our audience learned as much as I did today. All good things must come to an end, including this podcast. If I had to summarize our conversation, we have seen that the world of macroprocessing is fascinating. It comprises many processes used in almost all industries, from automotive and aerospace to medical. It is also very dynamic. From the first test of laser beam welding on steel a few decades ago to spatter-free copper welding and additive manufacturing, macroprocessing has changed since the very beginning. Beam shaping is part of this evolution. It improves the quality and yield and enables new processes which have been impossible up to now. We hope that we succeeded in sharing our passion for laser processing, and we thank you all for listening. Of course, if you want to know more about our technology, you can find everything you're looking for on our website. Also, you will find results of many applications we have addressed on our social media platforms, LinkedIn and Twitter. To finish, thank you very much, Guillaume. It's been a pleasure to discuss with you during those two podcasts about laser material processing.
Well, thanks, Julien. This is a shared pleasure as well. And thank you for having me in. And to all of you listeners, special thanks for listening, taking the time. And never forget that Skylabs can really help you share the light whichever applications you face.